more clips like this one and ring the bell for more thought-provoking content. Of all the objects in space, black holes are perhaps the most mysterious. At a basic level, we know they essentially absorb nearby light, which makes them invisible for the most part, meaning the presence of a black hole is usually inferred only via the effects its gravity has on close surroundings. It was the scientist John Michel who first theorized these incredible structures back in 1783, although the concept was then so strange that it was largely ignored until one Albert Einstein began his research more than a century later. Even then, it wasn't until the 1960s that the name black hole became widely used. Jump forward to today, and black holes still don't make a great deal of sense to modern minds, and even our surest equations break down when asking what lies at their center or at their singularities. So much so that even the concepts of a center or bottom of a black hole can't truly be taken literally. General relativity tells us that there's so much concentrated inside black holes that they actually warp space-time infinitely to create a never-ending pit in the fabric of space. Based on current thinking then, the bottom is never actually reached, although this is by no means a closed case, and our knowledge is changing all the time. What's at the heart of a black hole is more complicated than simply saying it's a singularity though, even if that is true. As per one approach, when we consider space-time, the theorized fabric of the universe, we then need to ask what type of singularity we're dealing with: spatial or temporal. Spatial or space-like singularities act differently to their temporal or time-like counterparts. In a spatial singularity, matter becomes trapped once it reaches the event horizon, at which point it literally has no future from a time perspective and no longer exists. However, in a temporal singularity, while post-event horizon matter again becomes trapped, its presence in time continues, and so that matter does still, to some degree, exist. The more mainstream line veers towards black holes housing a spatial singularity, as it has done for decades, but in more recent times, there have been questions raised, because on the one hand, temporal singularities might solve many of the problems surrounding black holes, turning them from the lifeless dead zones that we've stereotypically come to imagine them as into something much more alive, and perhaps even into a creative force themselves. However, temporal singularities would likely also be much more visible, which, for now, we know that black holes aren't. Perhaps it's only a matter of time before we find out that black holes are a matter of time too. But until then, research continues. Then again, some suggest that we may be wrong to focus so intently on singularities to begin with, and that it could be something else that's hidden in the black hole depths. Some then go as far as to say that our entire theory of black holes could be misguided. We know that, fundamentally, these objects don't exactly mesh well with most of the rest of our current theories on life, the universe, and everything. But according to one hypothesis, put forward by physicists Pavel Mazur and Emil Matula, that's because black holes aren't actually black holes as we currently understand the black hole concept. Instead, they're another immense space object called a gravistar. A gravistar looks exactly like a black hole from a distance, and, of course, from a distance is only ever how we view them anyway. But here, there's something different inside, and there could just as well be a bottom to reach. Instead of endless singularities, gravastars contain pools of our friend dark energy. So often, dark energy is put forward as an answer to the unanswerable because it remains a near total mystery to us as well. But when it comes to black holes specifically, or in this case gravastars, the natural repulsiveness of dark energy is key. In a gravistar, matter still falls past the event horizon and beyond our view, but it doesn't infinitely fall from there on in. Rather, it's repelled by a heart of dark energy and so rests around the gravistar core. To us, it's still lost, but to the universe, it's still there. Importantly, to date, this theory isn't especially widely supported, but it remains an intriguing possibility, and it hints at how one day we may well make discoveries about black holes that could totally change our understanding of physics. Moving even further out, some researchers entertain altogether different theories on how the universe itself works in order to explain how a black hole can exist within it. Loop quantum gravity is one such theory. It attempts to build an ever-elusive theory of quantum gravity by stating that the universe is actually made out of tiny chunks or loops in space-time. There are many other implications if this is true, but for black holes, it means that at their bottom, there lies something called a Planck star or dark star. In wider physics, the Planck length is the smallest possible unit of measurement, and as far as we know, objects can't exist that are tinier. The Planck star, then, is also almost impossibly tiny, but it's suggested within this model that it can still repel other energy, and therefore marks an effective endpoint for all things within a black hole. One potential problem with this approach is that it's been found that black holes in this scenario should explode after a short while, but we've never known this to happen. One potential get-around, though, involves the time dilation around the warped gravity of a black hole messing up their lifetimes so that, to us, they appear to last for billions of years. But again, these are ideas that are constantly evolving. For now, they represent another possibility, although the true nature of a black hole remains obscured. So what's your verdict? Each of these theories variously abandons our more traditional physics to serve up an answer, be that some kind of temporal singularity, a heart of dark energy, or a determined Planck star standing firm. Then again, these aren't your only options. According to the black hole cosmology model of the universe, for example, the interior of a black hole doesn't ever quite reach infinite density. Instead, the collapsing matter hits a breaking point, at which point it powerfully rebounds outwards. Only it doesn't rebound in our universe, but out in another one, creating something like a tunnel in space-time, thereby linking us to an altogether different plane of existence. Indeed, this might just be the most bizarre and speculative theory put forward so far. So keep your eyes peeled for an in-depth follow-up video, taking a closer look. Until then, what exactly lies at the bottom of a black hole unfortunately remains a mystery to us. And based on current knowledge and technology, it may be that we'll never be able to get close enough to one to totally understand them. Their secrets are well guarded, but they're